Thank you. So I'm Giorgio, I'm the CTO of Scality. It's a big chance you never heard of us, so I'm going to do a quick introduction. So we're not targeting consumer, we're targeting businesses who have a lot of data to store. So they need to have at least a petabyte of storage. So what we do is we take standard servers full of drives, so for example, 10 terabyte drives, and we pull them together as one huge pool of storage. So our software makes sense if you have a petabyte of storage. So we start at high scale. So the type of customers, on the right you have a list of people that are our customers. So Rackspace is an example, Comcast, Orange is in Europe. So it has to be people with a lot of data. So it's internet service providers, cable operators, TV stations, these kind of companies. And so we've been doing C code for a very long time. The company is 6 years old. And we had one day, one of our customers asked us for a prototype. And we thought we had 3 months to do the prototype, but we actually had 15 days. And so we looked at the engineering team, what can we do in our usual way of doing things in 15 days? And so nothing. We could not actually do anything. So I was looking at what are the options. So we have to do something that it was about processing video very quickly. So we call this a TiVo in the cloud. So it was about recording TV shows directly into servers in a data center, so that the consumer didn't have to store its own video locally. So no need for hard drive, it's all stored in the cloud. It was for 25 million users. So it's basically half an exabyte in 6 months in terms of amount of storage. And so we decided to do the prototype in Node.js because it was actually let's develop quickly, we can reuse our backends, but we need a front end that scales, and we have no time to do it in our usual way in C and a mix of assembly. So let's try Node.js to make it happen. So this was in 2014, and this was our first project in Node. So we had a very small team, we started working on this, and we actually got pretty good performance. So we got the system to scale to 30 gigabytes per second. So that's gigabytes, not gigabits. And to do that, we couldn't choose the network because the network was too slow. So what we did is had some Node.js proxies, take, for example, a TV show like HBO being recorded, send that to this machine and ask the machine to do 1,000 copies locally. So we had a farm of a lot of machines, and we were asking each of the machines to do copies, because for each consumer recording, it had to have its own private copy. Otherwise, you're not in compliance with the Hollywood IP law. Each customer should have his own private copy. So we did that prototype on 10 machines, 460 drives, so it's a lot of drives, and we got the 30 gigabytes per second. And the latency for each frame, because you're getting frames of a video, a few seconds that you have to expand on drive. We were around average 160 milliseconds and close to 500 milliseconds for the slowest piece. And so it was all okay because we had to do that in less than 10 seconds. So we actually got pretty good numbers. And so we went back to the engineering team, some of the guys in Paris, and say, oh, so we actually made it in Node.js. And when you talk to hardcore C developers, they kind of don't believe you to start with, right? so we decided, okay, so this is something interesting. So if we could do a prototype in 15 days, then our competition could do the same. So should we start investing in Node and have some of our development in Node and keep the core in C, but kind of accelerate our delivery and have some more Node.js? So we decided to build a team, and the team is in San Francisco. So these are the team members. We all look silly because it was a team building event where we were locked in a room with a zombie. And so that's when we escaped. So that's why we look funny. And so the team is in San Francisco, and we decided to build a new interface to our system that implements the AWS S3 protocol. So I don't know if you are familiar with AWS. The S3 protocol is an object store where you can store data in the cloud. So we decided to implement our own S3 interface so that our customer could store data in their data centers using the S3 interface. And so we decided to use Node The actual S3 stack is open source. We call it the S3 server. This is the code that got 100,000 downloads on Docker Hub. It was open sourced in July 2016, last year. And we also developed a distributed database because when you manage, the S3 protocol is made of bucket. You have a lot of policies, ACL, a lot of metadata to store. So we decided to build our own database because buckets are very peculiar. We can have billions of entries inside a bucket. They need to be geo-distributed. So we build our own, but also in Node.js. And we also build a security layer because you need to manage access keys, encryption keys, these kind of things. And we also build that in Node.js. We call it the Vault. So if you zoom on the open source itself, so the open source version is for a single machine. It doesn't scale out to a ton of nodes. That's our commercial version. But the architecture is this way. So you have a protocol stack. Then you have different drivers for authentication, for bucket management. So bucket is listing mostly, and for the data itself. And it's plugin based. So we actually have plugins for Docker to store your data and your buckets, plugins for our own software, our distributed storage system, and also plugins for things like AWS itself. So you can do hybrid storage, where some of your data is local, some of your data goes to Amazon, but all using the same interface, the same API code. So what can you do with this? It's basically useful for a developer who wants to code on a plane, actually do use it. So you have your own private S3 instance on your laptop, so you can do your own test, basically. It's good for CI if you want to stand up a very fast, low latency S3 service. We have a memory driver, so everything goes to memory. When you kill the container, you don't have any state to clean up. So it's kind of a good use case. And you can also go in production usage on one machine if you want to. So we reached this 100K. It was a surprise to us. Actually, it went pretty slow. It was a few thousand after 2 months, then 10,000. And it was between November and December that it really accelerated. So with Docker, we don't really know who pulls what. It's very opaque. But we're very happy about being able to reach that. And so we've done at least 15 customer proof of concept with this. And we have one huge customer that's in production today of 2 sites and multiple petabytes of storage. And so to be able to make this work, we learned a lot about optimization, a lot about debugging of Node.js. And so that's what we want to talk about. That's what we want to talk about today. So what have we learned, right? So one of the first issue we had is logging. So in our services, or our customer services, we're talking millions of users. So you have operations happening all the time. And we were using standard logging libraries for Node.js, like Bunyan, for example. And when you profile our system, it was only logging. Like 90% of the CPU usage was spent on logging. So we decided to do our own, even though I didn't want to. So it's another open source project we call Where Logs. The idea was to do as little processing in Node.js as possible. So send raw JSON to Elasticsearch, and not doing any expansion of variables. Like the time itself is a number. We send a timestamp. We don't try to expand it as a date in ASCII. We're trying to minimize the number of objects that we send. We try to minimize the number of allocation we do, just so that we can make sure that the logs are not taking that much performance impact on the platform. The other thing is, with logging, either you have too much logs or you have too little, right? And so we wanted to have something that gives us everything we need if there's a problem, and if everything goes okay, not having too much logs. So we implemented what we call log stacking. You can take a look at it in the open source, which is basically you have 2 log levels instead of 1. So you have a regular log level, let's call it normal. So if a request comes in, we're going to log not a lot, just enough that we know when it arrived, when it finished. But everything else, like debug and traces, we actually buffer them in memory. So we don't send them to Elasticsearch or to a file, but we keep them in memory. In case of an error, so you get some kind of callback in Node.js with an error, we're going to switch to another log level, which is log level when there's an error. And then you can go back to trace. So that for that particular connection, you're going to get all the traces you need to debug a specific customer connection. So if you look at Elasticsearch, everything is log level normal, not too verbose, not too much data. And on that particular connection that failed, you get all the traces you need to actually debug. So that's a client code that uses Verilog. The way that you would configure it is you have two levels. So level normal, that's debug, and a dump level, right? And when you start it, you give it both levels, and it manages that for you. And will queue in memory until it finds a critical error, and then it dumps everything for that connection only. So it's also implementing a way to actually forward log request ID between components. So we have a microservice architecture, so we have a lot of components. When a front end talks to a back end component, it's actually sending log ID, a request ID, so that we can trace a request from the beginning to the end, because they all use the same ID for a particular HTTP request from the client. So in the particular trace, you can see that it hit our S3 front end, then it went into a proxy, then it went to Nginx, another proxy, our metadata layer, and so on. And you can trace one connection for the entire stack using a global unique ID. So this was a big saver for us, because at the beginning, all our performance was inside logging. So after that, it's all about performance. In our case, our customer deploy a lot of hardware, and they don't want to waste any CPU resources. So we spend a lot of time improving performance. So I'm going to share a few of the things that we did to kind of improve performance. So it's actually a performance cycle. You code something, you want to make sure that it didn't slow you down. So part of a continuous integration test is to check for performance non-regression. So one thing that I don't know if you're familiar with the Nago algorithm. It's a kind of an optimization where when you send a small message on a socket, it's not going to send it right away. It's going to wait for having more data before sending a bigger packet. So it's very useful if you want to reduce the amount of traffic on your network in case you have large packets. In our case, our metadata layer is exchanging very small, like 100 bytes, 200 bytes object. And so it was slowing us down, because basically you write on a socket, the data doesn't leave until the Nago algorithm gives enough time, a timeout before sending. So disabling this really improved our latency. So we just couldn't understand where the latency was coming from, right? Not doing anything complex, it was just adding milliseconds of latency for no reason. And disabling Nago on our metadata sockets, not the data sockets, just for the metadata, so small amount of data, really improve performance. Then the event loop. So the worst thing that you can do is call an expensive function in the event loop, right? And so we have a lot of checks in place so that we can know if this happens, because this impacts all your connections, right? So if you have 1,000 connections on one machine, and one of them is doing some, I don't know, open SSL encryption, or some AES encryption, or whatever, on the main event loop, or opening a file, like using a file sync function, like open sync or close sync, you're blocking everybody else, because you're blocking the event loop, and everybody, all the other connections suffer. So really fight to make sure that you don't have CPU consuming tasks in the node main event loop. Then you have to hunt for all the strings and replace them with buffers, right? So we manipulate some large data object. It could be one file, could be multiple gigabytes. And each time in the code where you get a buffer and you make it a string by doing a concatenation, what you're forcing Node to do is to allocate a new, bigger string, then copy data from the old one, copy data from the new one, and make it a bigger string, right? If you do that 1,000 times, you're actually wasting so much useful CPU and memory. So you have to hunt for all the strings, all the concatenation, replace them with buffers, arrays of buffers, and never concatenate until the last minute when you actually need to do it, right? So this is a big performance difference. Buffer concat itself has a parameter which is you can give it if you have an array of buffer, you want to make it one large buffer. You can give it a size, the length of the destination buffer. When you do that, it's much more efficient because otherwise he has to scan through all the buffers to know the size and then build a bigger buffer and copy the data. So just adding the length is night and days in terms of performance. We had a date object everywhere in the code. Just transforming them to a date.now made a huge difference because creating a date object actually does some system calls and takes some time and wasted a lot of garbage collection and allocation of objects. So just this small change, which looked like a micro optimization, had a huge impact in the end. And libraries. It's so easy to import, require something, or change your package JSON, and then you don't know what's happening. It's library hell, right? And so we had to be careful and try to import the minimum. And sometimes you import something that looks very simple. It's actually a NaN module that's going to start threads in the background and that's going to impact UV and the core engine of Node. So you have to be very careful and not import stuff that you don't need, right? And the way to catch these things, because there's just so many ways that a developer can slow down a system, you need to check for performance all the time and make sure that there's no performance regression so that you can catch these bugs pretty quickly. So the developers wanted to use ES6 early on, which I think is a pretty good idea. The way that we did it with Babel 5, Babel 5 was adding a lot of crap, basically. A lot of glue code that doesn't do much, but that was impacting performance pretty hard. And so upgrading to Babel 6 made a huge difference in performance. Because on Babel 6, you can actually specify which extension you actually need, and you have much less unnecessary glue code in your actual compile code. So Babel 6 was a big win. So what kind of performance do we get in the end? So this is on one instance of the S3 server code. Going through 6 metadata nodes, or 5 metadata nodes. Here we're looking at the actual S3 server performance. So if you look, I don't know if you can see something, yes. So if you look at the this first line, so this one is with one connection, and after it's two connection, 4, 8, 16, we're just doubling each time, right? What you can see is on one connection, this is a write operation, and we're getting 6 milliseconds per operation, which is pretty good, and around 150 operations per second. So it took us a long time to go down to 6 milliseconds, and that's removing all the dates, removing the logs, making sure we don't import stuff we don't need. Oops, sorry. And then as you increase the number of connections, I can jump to this one, which is around 64 parallel connection. We're getting 2,000 operations per second, which is a pretty cool number. But these 2,000 operations come at a cost, which is increased latency, because now you have 126 milliseconds of latency. So the good news is with Node, you can always push more load, and you will see more operations per second, but you actually always increase latency a little bit. And you see it because your CPU process is at 100%, you're consuming all the resources. You can still send more traffic, but it's going to be slower and slower in terms of latency. So the way that we size our system is we push it until the latency is way too high, and then we scale back to something like 20 milliseconds latency, which we think is acceptable. And so that gives us 1,500 transactions per second, which is a pretty good number. So basically, we size for 20 milliseconds latency, and we know that if there's a burst of traffic, we're going to be able to absorb it and go up to 2,000 operations per second, and the latency will be higher for a small amount of time. But in nominal case, you have good latency. So read is the exact same story. Look at the latency, 2 milliseconds, pretty good, 450 operations per second. You increase the number of threads, you go to 4,200 operations per second, 80 milliseconds latency. So you go back to 20, which is kind of a sweet spot, and that gives you 3,000 operations per second. So that's on one instance. So we're pretty happy with the numbers. right? Because that means that we can manage a lot. And some of our customers deploy thousands of instances. So if it scales linearly, you're looking at millions of transactions per second, which is our target. Okay. Debugging, you know, when you talk to C developers, they're used to GDB, they're used to Valgrind, they used to be able to debug a system and print anything they want. It was hard for us not to have a debugger on Node to start with. Because we used to, you go in production, the system is behaving funny, you connect to it via GDB, you do some stack traces, you print some stuff, and you understand what's happening. And so recently we found LLDB, which is from the LLVM project, and LLDB has a Node plugin, and this is amazing. So you can attach to a running process, or you can debug a core that you made, and then you can print all the JavaScript objects. Right? So this is a running process, and you see all the objects. So there's some HTTP parser object, there's some error object, the number of objects is on the left. And for each of these object type, you can list all the individual references, print them, zoom into callbacks, and you can really manipulate the Node JavaScript interpreter any which way you want. So it's very, very useful for debugging. The other tool that we use is strace. I don't know if you're familiar, which is more of a Linux sysadmin C type of tools, more than Node. But it's very useful to debug kind of system level issues. Like you forgot to close something, you're coding the same function in a loop. And so the good news with strace is we can attach to a running process. We don't have to stop the system. And the actual performance impact is pretty low. So it's an example of an strace where we had, so it's an issue that's open on Node.js GitHub that we opened actually, where we have some processes that get stuck in a loop and consume a lot of CPU. And so the first thing that was asked is, what are they doing? So the strace to a running process shows me that they are stuck into equal wait, which is a system function to detect if a socket has changed. And so we could clearly say that the issue is that they're spinning in that equal function, because strace was sending us equal wait pages and pages. So there's low impact on performance, and it's a quick way to know what your process is doing. So kind of our support people, if they log into a production system and something is taking too much CPU, they'll do an strace on the process, and with 10 lines, we know exactly what's happening. Right? So I think that's something that's very useful. And then you can go from there to using LLDB if you want. If you need to print some stuff, at least with strace, you know where to look at. Because in LLDB, there's so many objects, you don't know which one to look. So from strace, you know it's network related, so you can go back and print socket object. Right? Okay, and I'm welcoming Lauren to talk about tools.
Thanks, Giorgio, and thank you so much, Matt, for having us here and for Shutterstock. I don't know if Giorgio mentioned we're from SF, and it's pretty cool to be able to come to a Node meetup somewhere away from home. So I'm going to talk about some of the tools we used in developing this project, and it's an ongoing evolution. So if you have any tools that you like, I'd love to hear about them. First, there's Node Core, which offers amazing modules, and I'll talk about two really quickly. Streams are essential. Whenever you can use streams, use them, make your own, expand on them. They really improve performance, and they're actually fun to work with. Also, the cluster module really comes in handy. You don't play with it much. You set it up once and you're done. But it makes it so you can have many processes running. So JavaScript single-threaded, but you can start running multiple processes, and they're independent. So if one crashes, you have your other workers going, and you can respawn a worker in a new process. So it's fundamental to stepping up your game and not wasting resources and CPUs. Okay, so when we were getting this project going, we could have argued for years about what style would be good. Instead, we just went with the Airbnb JavaScript style guide and ESLint, so we could just move ahead and have clean-looking code, and everyone's writing the same stuff. I've also heard good things about standard, I believe. Giorgio mentioned that Babel really came in handy because we started the project right around when const and let and Lambda functions were being used by Babel, but not by Node Core. And if we had just stayed with the old vars, we would now be involved in a huge refactoring project. Instead, we used Babel 5, which transpiled everything, kind of killed performance. At some point, we were able to move to Babel 6, and at this point, we're actually only using Babel 6 for imports, which won't impact performance at all because that's all run at startup. Though I should note that an operations guy from our company actually hip chatted me at 9 o'clock at night a week ago to tell me that I was killing our whole cloud where we have testing and demo VMs because I had a whole S3 system just kind of restarting over and over, and when Babel runs, it takes up a ton of CPU. So I killed that and saved the day. Commander is kind of a fun tool if you haven't played with it to make CLI tools in minutes. And then it's JavaScript. You have to figure out what do you do with the asynchronous calls, and we actually use the async module for our production code, and then Bluebird promises for setting up tests, which had multiple steps. Pure callbacks with async has better performance, and the code, in my view at least, was kept pretty clean. So then other things when we were diving deeper into the project, we're using LevelDB for our metadata layer, and being Node, the great community it is, there's already a wrapper straight off NPM. Same with memcached. We had this situation where a customer wanted to use the product sort of not how intended, and using memcached enabled us to do a proof of concept meeting their goals, which really surprised everyone. The performance was amazing, and I was able to implement this whole caching layer in an afternoon in a coffee shop. It was pretty cool. But you have to be careful about what modules you're using. We were using an XML generator to generate XML, and that sort of was useless and causing us to take a performance hit. So instead, we just create our own XML through pushing strings and making sure we're escaping any bad characters. But for parsing, yeah, we use a module. As Giorgio made clear, we are obsessed with performance, so we profile a lot. And yes, we test our code. We use the basics, Mocha, Istanbul for coverage. Lolex is fun to bend time to your will. And since we are building an S3 emulator of sorts, the Node SDK is used for a lot of our functional tests. I don't know if people actually think of this as a tool usually, but docs are actually a good tool, and the Node docs are actually very good if you have a problem. But I found even better the fact that the source code is available. The source code is really readable, and if you don't know how something works, then if you go and just actually pull the code and look at it, you're going to figure out how to do something that you didn't think you could do before. So, demo time. What can you do with this thing? Oh, that's the Docker page. So for a demo, I thought it would be cool to do Heroku actually has a sample Amazon S3 Node app on their site, which you can clone. And so I did that, and it's basically just really simple. How do you store objects on S3 that you'll need for a web app? So I forked that repo, Node Direct Uploader, and in order to use it with our code rather than AWS S3, all you really have to do is, when you're instantiating your client, use whatever your Scality endpoint is, which for us it's going to be localhost 8000, instead of just whatever AWS region you'd be calling. So that's what this is doing. And that's really all I had to do to the code, other than it was also calling S3 Amazon AWS here, and so I fixed that. And what this pretty simple skeleton app is doing is it's creating a signed URL so it can send an authenticated request to AWS S3, but also Scality S3 to put an object in the bucket as public read so that the app can then get it back again. So let's see how it works. I'm going to start, just write locally an instance of the S3 server. So you can run in Docker, you can run it locally. It's really awesome if you have to test against S3 because you can just run this in memory and do whatever you want to do. You don't have to pay any charges. You don't have to like sign up for an account on AWS. You don't have to give them a credit card, blood type, nothing. It's just running. To start the upload, the Node Direct uploader, you have to give it credentials, and our default credentials are the very secretive access key 1 and very secret key 1. So that's all I have to give it there. And then it wants the name of a bucket. So I'm going to start up this app, and then I'm going to go into CyberDuck, which is just a really light GUI for S3, and create that bucket. So I called it Pix. So now we have our Pix. Oh, shoot. I didn't restart this. I'm sorry. Let's make this really live. Let's make sure we are creating a brand new bucket. So I'm going to create Pix2. There we have it. It is empty, as expected. Then we're going to go to localhost 3000, which is running our very stylish, very well-styled Node Direct uploader. And what it simply does is, you can upload a picture and save it in the S3. So like if you were running, say, a Shutterstock and you need somewhere to save lots and lots of images and data, S3 would be a good choice, as would the Scality S3. So that's what we're going to do here. One thing before we do that, because it's using front-end JavaScript code, we need to set our bucket to have cores enabled. So to do that, all you do is make a call where you send it a cores configuration, which I'm going to do now. But it wants my old bucket name. So that's done, and so that you can see what that configuration looked like. Let's just do that. So it's a really simple cores rule where I'm just allowing any origin to send requests to get, put, or post. All right, it's time to upload. So choose a file, and I think maybe, no offense to anyone, but we've seen enough cats tonight, so we're going to see an otter. And there he is. So this this guy is now just an image in our bucket. So if I refresh CyberDuck, you'll see this thinking otter, and it's just an image that's being pulled. And if we don't like one otter, we want something cuter, we can always just change our profile pic to a group of otters. And that, as you'll see, is just another image in our bucket. So that's how it works. We have multi-part upload, put, get, delete, multi-object delete. We now have bucket website, cores. Our API coverage keeps growing. And actually, at this point, we're starting to get more creative. And we're actually expanding on what S3 does in our own S3. So we're implementing kind of our own Lambda functions. So if you like to use image magic and you're uploading an image to S3, you can like modify it before it gets saved. You can check whether it has some attributes you want before it gets saved and just reject it. You can do all sorts of things, and that is available on AWS S3 using their Lambda capability, which use the different services. Here it's actually really simple. You can write your JavaScript codes. That's the idea, and using Node streams as well to make everything efficient and run. Also, in the pipeline is a two-server distributed fault-tolerant option. We'll have two metadata and data backends running, so if you lose a server, the process will still remain, and you can still keep getting and putting data. We also are working on an option where you have multiple backends, so say you want to save to your Scality S3 and you want to save data to your real AWS S3, and at some point even we're thinking of Microsoft Azure, so you can in one place, have all your metadata for all your objects, but distribute out where your actual data is being stored. We're working on that feature as well. And we would love to know what would excite you, because this is an open source project, and we can take it in many ways. We're a full development team working on this, and we'd love to hear what ideas you have. So if you want to download the code, you can find our splash page. You can go right to GitHub, or you can go get the Docker container. And this is how you reach us. Questions? Yeah?
Question about the debugging in general. Do you feel that your team's prior experience with C helped you find these methods of debugging, or this team was purely Node specific?
Actually, the most recent iteration on the debugging was from posting an issue into the Node repo. So actually the Node community stepped up to help find the right tools. Though I would think that then going deeper into GDB, that involved this, like, people who have a lot of heavy C experience.
Yeah, I think. Oops. Well, I'll leave it here. Yeah, to be completely honest, I think the C actually hurt because the guys kept thinking it was a Node core issue. So somebody wrote some code that is messed up in Node, and the C guys that are switched to Node immediately go in the Node.js code and say, oh, it's a bug in Node.js. So we had that kind of attitude a lot at the beginning. And then they do GDB, but it's a higher level issue. Now that we are at scale, we have a lot of networking issues, and it's good that we have a C background, because then we can look at the sockets and all these things. So it hurt at the beginning, and it's useful now.